the light had been traveling for 13 billion years. It left its galaxy when the universe was a tenth of its present age, a young cosmos still thick with forming stars, and it crossed a darkness that was not empty but growing. Space was stretching. The wavelength of the light stretched with it, from ultraviolet to blue to green to red and then beyond red, into the infrared and the microwave, a steady, silent elongation that took it from a single hot point of emission to a faint whisper, arriving now at a radio dish in a desert on a small planet. The photon carried no information about where the universe was expanding into, because there was nowhere to expand into. The universe is not a bubble, inflating inside a larger room. It has no edge, no boundary, no outside. The question of what it is expanding into is like asking what lies north of the North Pole. The photon has never been anywhere but inside space, and space has never been inside anything else. That is the answer. It takes about 40 words to state, and most of a lifetime to actually believe. Tonight we are going to spend some time with the expansion of the universe, how it was discovered, what it actually is, and what it means for everything that will happen from here. Before we begin, if you find this kind of slow exploration useful for sleep or for winding down, a like or a subscribe genuinely helps, and I am always curious where people are listening from. Drop your location and the time where you are in the comments. Here is the question that will carry us through the night. If the universe is expanding and there is nothing outside it for it to expand into, then where is all this new space coming from? By the end, that will not be an abstract statement you have agreed to. It will be something you can hold. Let us begin. You are moving at over 2 million kilometers per hour. That is the speed of the Milky Way relative to the cosmic microwave background, the oldest light in existence, which serves as the closest thing the universe has to a frame of rest. The Sun is carrying the solar system around the center of the galaxy at roughly 828,000 kilometers per hour. The galaxy itself is falling toward the Virgo cluster. The whole local group of galaxies is being pulled towards something in the direction of the constellation Centaurus. Stack all of those motions together, and you arrive at a speed of about 2.1 million kilometers per hour with respect to the ancient light. You cannot feel any of it. There is nothing to feel it against, but the motion is real. It has been measured to a precision of a few kilometers per second, and it has been happening for every second you have been alive. None of that, however, is what we mean when we say the universe is expanding. The expansion is a different kind of motion, and the difference is the single thing most worth getting right tonight. Galaxies are not flying outward through space from a central point, the way debris flies from an explosion. If that were true, there would be a place the explosion happened, a location you could point to, and the further you traveled from it, the emptier things would get. That is not the universe we live in. What is happening is that the space between galaxies is getting larger, not the galaxies, the space. The standard way to see this is with a rubber band. Draw a row of dots along its length and then pull from both ends. No dot travels along the band. Every dot stays exactly where it was drawn, but every dot now finds that the distance to every other dot has increased, and a dot 10 centimeters away recedes twice as fast as a dot 5 centimeters away, because there is twice as much rubber between them, and all of it is stretching at once. That last detail is the whole of it. The further away something is, the faster it appears to recede, and the relationship is a straight line. Double the distance, double the speed. That proportionality is what tells you that you are looking at stretching rather than at motion, and it is the single most important measurement in the history of cosmology. It also means there is no center. Stand on any of those dots and the view is identical. Every other dot moves away from you, the distant ones faster than the near ones, and you appear to sit at the still point of a fleeing universe. Every dot appears to sit at the still point. There is no location where the expansion began, because it did not begin at a location. It began everywhere, simultaneously, and it is still happening everywhere, including in the room you are lying in right now. The way we measure it is through the color of light. When light leaves a distant galaxy, it leaves with a specific set of wavelengths, and those wavelengths are not arbitrary. Hydrogen absorbs and emits at precise frequencies. So does calcium, sodium, iron, helium. Spread the light of any star into a spectrum, and you get a rainbow crossed by dark lines, and the pattern of those lines is a fingerprint. It is the same pattern in a laboratory in Zurich as it is in a galaxy 4 billion light-years away, because the physics of a hydrogen atom does not care where the atom is. So when astronomers photograph the spectrum of a distant galaxy and find that the entire pattern has slid toward the red end, they are not guessing. They are measuring, precisely, how much the light has been stretched between emission and arrival. That measurement is called redshift. Here is where the intuition usually goes wrong. It is tempting to treat redshift as a Doppler shift, the way an ambulance siren drops in pitch as it passes. That is a real effect, and it does happen, but it is not what the cosmological redshift is. A Doppler shift happens at the moment of emission, determined by how fast the source is moving at that instant. The cosmological redshift accumulates over the entire journey. The photon does not get stretched once. It gets stretched continuously, for billions of years, by every meter of expanding space it passes through, which produces a fact that is easy to say and difficult to sit with. A photon with a redshift of 1 has had its wavelength doubled, which means the universe has doubled in size since that photon was emitted. Not the galaxy grew, not the photon slowed. The universe is twice the size it was. The redshift is not really a measure of speed at all. It is a measure of how much the universe has grown since the light set out. The galaxy that emitted that light may not exist anymore. Its stars may have burned out, its gas exhausted, its shape torn open by a collision that happened 4 billion years ago. None of that reaches the photon. The photon simply keeps going, carrying an increasingly stretched record of a moment that has long since passed, until it lands on a detector and a person writes down a number. The observable universe, meaning the region from which light has had time to reach us, is about 93 billion light-years across. That figure surprises people, because the universe is 13.8 billion years old, and it seems that light could only have covered 13.8 billion light-years in that time. But the space the light was crossing kept expanding while the light was in transit. A photon that left its galaxy 12 billion years ago has been climbing a road that has been lengthening underneath it the entire way. When it finally arrives, the galaxy that emitted it is not 12 billion light-years away. It is far further because the intervening space has grown enormously since the light departed. So the number is not a contradiction, it is a consequence. And beyond that 93 billion light-years, the universe almost certainly continues. Possibly a great deal further, possibly without limit. If it is genuinely infinite, then it has always been infinite, including at the moment of the Big Bang, and the expansion has simply been increasing the distances between points inside an infinity that was already there. Stretch an infinite number line, and the gaps between the numbers grow. The line does not become longer, because it was never any particular length. It just becomes less dense. There is no edge. There is no boundary. There is nothing outside. That is easy to assert and very hard to accept, because every instinct you have was built by a species that evolved among containers. Rooms have walls, bodies have skin. Everything that grows in ordinary human experience grows into something, displacing air or water or soil. The universe does not do this, and the reason is not that it is expanding into something we cannot see. The reason is that space is not a substance sitting inside a larger arena. Space is the arena. When it expands, it is not filling anything. It is generating distance where there was less distance before. How we came to accept that, and what it cost the people who first said it out loud, is a story that does not begin with a theory. It begins with a man alone in a cold wooden dome in Arizona, photographing light that would not stay where it was supposed to be. The Lowell Observatory sits on a ridge above Flagstaff, Arizona, at about 2,200 meters of elevation, in air that is thin, dry, and unusually steady. It was built in 1894 by Percival Lowell, a wealthy Bostonian from a family of poets and industrialists, and it was built for a specific purpose. Lowell was convinced that Mars was crossed by a network of artificial canals, dug by a dying civilization to move water from the polar caps to the equator. He was wrong. The canals were an artifact of the human eye, straining at the edge of resolution, assembling faint smudges into straight lines, because straight lines are what human vision reaches for when the data runs thin. But the observatory was real, and the instruments were good, and in 1901, Lowell hired a young man from Indiana named Vesto Slipher. Slipher had a fresh degree in mechanics and astronomy, and no particular reputation. He was hired on a temporary basis. He stayed for 53 years, and eventually became director. He was quiet to the point of severity, meticulous with instruments, and almost pathologically cautious about claiming more than his data supported. That last quality would shape everything that followed. In 1909, Lowell gave Slipher an assignment that flowed directly from Lowell's obsession. The spiral nebulae, those faint whirlpool smudges scattered across the sky, were in Lowell's view solar systems in the act of forming, clouds of gas condensing into planets. If Slipher could photograph their spectra, he might catch the chemistry of planetary birth, and that would support Lowell's whole picture of a universe busily manufacturing worlds and civilizations. The assignment was based on a mistaken premise. It produced one of the foundational measurements in the history of science. That happens more often than the tidy version of scientific history admits. The instrument was a 24-inch Clark refractor with a spectrograph attached, and the work was brutal. A spectrograph takes the light of an object and spreads it out, which means the light that was already faint becomes faint, spread across a strip. The spiral nebulae are not point sources. They are large and dim, diffuse enough that most of their light misses the slit entirely. Slipher rebuilt the spectrograph to work with faster optics, and even then, the exposures ran for 20 hours, 30 hours, 40 hours, accumulated across multiple nights, with the plate left in place and the dome closed at dawn and reopened the following evening. For those hours he sat in an unheated dome at 2,000 meters in an Arizona winter, one eye at a guiding eyepiece, hand on a slow-motion control, correcting for the rotation of the Earth, holding a faint smudge of light precisely on a slit no wider than a hair, for as long as his body would allow. If his attention slipped for a few minutes, the exposure was compromised. If clouds came in, the night was lost. In September of 1912, he developed a plate of the Andromeda Nebula and measured the positions of the spectral lines. They were in the wrong place, all of them, shifted together, toward the blue. Slipher repeated the measurement. He took further plates. The shift was consistent, and when he converted it into a velocity, he got about 300 kilometers per second, approaching. It was, by a wide margin, the largest velocity that had ever been measured for any object in the sky. He did not know what Andromeda was. Nobody did. But whatever it was moving toward us at a speed that nothing in the known universe had any business moving at. He kept going. Over the following 2 years, he added nebula after nebula, each one costing him weeks. And a pattern emerged that he had not been looking for and did not entirely want. Almost all of them were moving away. By 1914, he had 15 spiral nebulae, and he presented them at a meeting of the American Astronomical Society in Evanston, Illinois. He read out the numbers in his flat, careful, unemphatic way. 3 of the 15 were approaching, including Andromeda. The other 12 were receding, at hundreds of kilometers per second. When he finished, the astronomers in the room stood up and applauded. It is worth pausing on that, because standing ovations at technical meetings are not common, and this one was for a table of numbers with no theory attached. The audience had understood something that Slipher himself refused to state. Sitting in that room, listening, was a graduate student named Edwin Hubble. By 1917, Slipher had 25 objects. 21 of them were receding. The fastest was pulling away at about 1,100 kilometers per second. For the next decade, almost every measured velocity of a spiral nebula in the world came from one man in one dome in Arizona. And there were years when the number of people on Earth capable of making that measurement was exactly 1. Slipher never claimed to know what it meant. He was a spectroscopist. He measured what the plates showed, and he stopped there. And when others later built the expanding universe on top of his numbers, he did not step forward to claim a share. He went on running the observatory, and in 1929 he hired a farm boy from Kansas named Clyde Tombaugh to search for a 9th planet. Tombaugh found Pluto the following year. What Slipher had was half of an answer. He knew how fast the nebulae were moving. He had no idea how far away they were, and without distance, velocity is just a curiosity. The other half came from a woman who never operated a telescope. Henrietta Swan Leavitt was born in Lancaster, Massachusetts, in 1868, the daughter of a congregational minister. She studied at the institution that would become Radcliffe College, and in her final year, she took a course in astronomy. An illness after graduation left her progressively and then almost completely deaf. In 1895, she began working at the Harvard College Observatory as a volunteer, and later for 30 cents an hour. The observatory under Edward Charles Pickering had an industrial problem. Photographic plates were accumulating faster than anyone could analyze them. Hundreds of thousands of them, glass, each holding thousands of stars, each requiring careful measurement of position and brightness. Pickering's solution was to hire women whom he could pay roughly half what a man would demand to do the analysis. They were called computers because computing was what they did, and there were eventually more than 80 of them. They were not clerks. Williamina Fleming had arrived as Pickering's housemaid and ended up discovering the first white dwarf and cataloguing more than 10,000 stars. Antonia Maury built a classification scheme subtle enough that it later revealed the difference between giant and dwarf stars. Annie Jump Cannon, who was also deaf, personally classified around 350,000 stellar spectra and devised the system astronomers still use today. Leavitt was given the variable stars. She worked in a quiet room with a magnifying loupe and stacks of glass, comparing plates of the same patch of sky taken on different nights, looking for points of light that changed. She found around 2,400 of them over her career, roughly half of all the variable stars known at the time. In 1908, she published a paper on 1,777 variables in the Magellanic Clouds, the two small companion galaxies visible from the southern hemisphere. Buried near the end was an observation she flagged as worth noticing. Among a particular class of variable, the Cepheids, the brighter ones seemed to take longer to complete a cycle. She spent 4 more years on it. In 1912, she published the result properly, using 25 Cepheids in the small Magellanic Cloud, and it was clean enough to be almost startling. Plot the logarithm of the period against the brightness, and the points fall on a straight line. The reason this mattered is subtle, and it is worth going slowly. Ordinarily, a bright star in the sky tells you nothing, because it might be a modest star nearby or a monstrous star very far away. Brightness on its own is useless. But all of Leavitt's Cepheids were in the small Magellanic Cloud, which meant they were all at essentially the same distance from Earth. Their differences in apparent brightness could not be a distance effect. They had to be real differences in the stars themselves. So the period of a Cepheid tells you its true luminosity. And once you know a star's true luminosity, comparing it to how bright the star appears gives you the distance by nothing more complicated than the fact that light dims with the square of how far it has traveled. That is a ruler that works across millions of light years on any object containing a Cepheid anywhere in the sky. Before Leavitt, astronomers could measure the distance to a few thousand nearby stars by parallax and nothing beyond. After Leavitt, the ruler reached as far as the telescopes did. The paper carries Pickering's name at the top. It opens by stating that the following work has been prepared by Miss Leavitt. She was moved off the variable stars afterwards and assigned to other work. She was never given a research position or a graduate student or an instrument of her own. She died of cancer in 1921 at the age of 53, in the year that her ruler was being used to redraw the size of the universe. And 4 years later, a mathematician named Gösta Mittag Leffler wrote to Harvard asking for details about her work, because he intended to nominate her for the Nobel Prize. He was informed that she had been dead since 1921. The prize is not awarded posthumously. The nomination was never made. So by the early 1920s, the two halves existed. Slipher's velocities sat in the Astrophysical Journal. Leavitt's ruler sat in a Harvard circular. Nobody had put them side by side, partly because doing so required the largest telescope in the world, and partly because it required someone with the particular kind of ambition that does not mind being the person who says the enormous thing out loud. Edwin Hubble was, by most accounts, a difficult man to be around and an impossible man to ignore. He was born in Missouri in 1889, grew up in Illinois, and was a genuinely gifted athlete, a high jumper and an amateur boxer, good enough that people occasionally suggested he turn professional. He won a Rhodes Scholarship to Oxford, where he read law rather than science, apparently to satisfy a promise to his father. He came home with an English accent that he never dropped, a habit of wearing +4s and carrying a pipe, and a small collection of stories about his own life that later biographers were unable to verify. He briefly practiced law in Louisville, or said he did. He taught high school Spanish and physics and coached basketball. Then he abandoned all of it, returned to the University of Chicago, and took a doctorate in astronomy at the Yerkes Observatory. He finished his thesis, enlisted, and spent the end of the First World War in the army in France. And when he was offered a position at Mount Wilson in California, he arrived still wearing his uniform. Mount Wilson had the 100-inch Hooker telescope, completed in 1917, which was at that time and for the next 3 decades the largest telescope on Earth. The question waiting for him was the one that had divided astronomy for a century. What are the spiral nebulae? In April of 1920, 2 astronomers had argued it out in front of an audience at the Smithsonian in Washington, in an event that has come down to us as the Great Debate. Harlow Shapley argued that the Milky Way was enormous, that it constituted essentially the entire universe, and that the spiral nebulae were nearby clouds of gas within it. Heber Curtis argued that the Milky Way was smaller than Shapley thought, and that the spirals were island universes, separate galaxies at vast distances. Each man was right about half of what he claimed. Neither had the data to settle it, and the debate ended, as such things do, with everyone leaving convinced of what they had walked in believing. The instrument that settled it was the 100-inch, and the method was Leavitt's. On the night of the 5th of October, 1923, Hubble exposed a plate of the Andromeda Nebula. He was hunting for novae, stars that flare suddenly and then fade, and he found what he took to be 3 of them. He marked each with the letter N in the corner of the plate. He compared it against earlier plates of the same field. One of his 3 novae had been bright before, and dim before that, and bright before that. It was not a nova, it was a variable star, and its light curve had the unmistakable shape of a Cepheid. He crossed out the N and wrote, in red ink, the letters V-A-R and an exclamation mark. That plate still exists. The correction is still on it. The period of the star was 31.4 days. Leavitt's relation converted that period into a true luminosity, and comparing that luminosity against how faint the star actually appeared gave a distance of roughly 900,000 light-years. The figure was too small, for reasons that would take another 30 years to uncover, but it did not matter. Shapley's estimate for the entire diameter of the Milky Way was about 300,000 light-years. Hubble's star was 3 times further away than the whole of the known universe. Andromeda was not in our galaxy. It was another galaxy, comparable to ours. And the spiral nebulae scattered across the sky in their thousands were other galaxies too. And the Milky Way was one object among an unguessable number of similar objects, in a cosmos larger than anyone in the room had budgeted for. Hubble wrote to Shapley with the result. Shapley read the letter, handed it to a graduate student standing nearby, and said that this was the letter that had destroyed his universe. The result was announced on the first day of 1925, at a meeting in Washington. Hubble did not attend. His paper was read out on his behalf. The next step required velocities, as well as distances, and it required them for objects far fainter than anything Slipher had managed. That work was done by a man who had left school at the age of 14. Milton Humason had come to Mount Wilson as a mule driver. During the construction of the observatory, every component of the telescope and every sack of cement had to be brought up the mountain on the backs of animals along a narrow trail, and Humason drove the mules. He married the daughter of the observatory's engineer. He took a job as a janitor. He asked to help out at night, and the staff, noticing that he was careful and patient and had extraordinarily steady hands, let him. He became a night assistant, then a full member of the scientific staff, and eventually one of the finest observational astronomers of his generation, with no formal education past the 8th grade. What Humason could do was hold an exposure. He would guide a faint galaxy onto the slit of a spectrograph and keep it there for 2 nights, 3 nights, occasionally longer, returning to the same plate evening after evening, and he did it well enough that the spectra he produced remain usable. He measured redshifts that nobody else on Earth could have obtained. By the middle 1930s, he had pushed out to galaxies, receding at 40,000 kilometers per second. There is a story about him that is probably true. Years before Tombaugh found Pluto, Humason had photographed the region of sky where Pluto was, and the planet was on his plate. It sat directly on top of a small flaw in the emulsion. He missed it. Hubble had distances. Humason and Slipher had velocities. In 1929, Hubble put them on the same graph. The paper is 6 pages long. It is titled, "In the Dry Manner of the Period, as a Relation Between Distance and Radial Velocity among Extragalactic Nebulae." It contains 24 galaxies, a scatter of points, and a straight line drawn through them. The line goes up. Further galaxies recede faster, and the relationship is proportional, and the slope of that line is a number that describes how fast the universe is growing. Hubble's value for that slope was about 500 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of distance, a galaxy recedes about 500 kilometers per second faster. That number is wrong by roughly a factor of 7. The modern value is somewhere near 70. The error was not in Hubble's care, which was considerable, but in the ruler itself. It took until 1952 to find. Walter Baade, a German astronomer working at Mount Wilson during the war, had an unusual advantage. Los Angeles was under blackout conditions, and for the first and last time, the sky above the observatory was properly dark. Baade used the conditions to resolve individual stars in Andromeda, and he realized that Cepheid variables come in 2 distinct populations, formed at different times, with different chemistry and different intrinsic brightness. Leavitt's stars in the Magellanic Clouds and Hubble's stars in Andromeda were not the same kind of object. The calibration had been off from the start. Baade announced the correction in 1952, and the universe doubled in size in a single afternoon. This mattered more than a tidy revision of a constant, because Hubble's original number carried a serious problem. If you take the expansion rate and run it backwards, you get an estimate for how long the universe has been expanding. Hubble's 500 gave an age of about 2 billion years. Geologists, meanwhile, had been dating rocks by radioactive decay and were confident that the Earth was older than that. The universe appeared to be younger than the planet inside it. For 20 years, that contradiction sat in the literature, and it was one of the strongest arguments available to anyone who wanted to reject the expanding universe altogether. Baade's correction did not resolve it entirely, but it removed the worst of it, and Alan Sandage spent the following decades grinding the number down further. What is striking about Hubble's own paper is what it does not say. He does not claim that space is expanding. He does not use the word. He refers throughout to apparent velocities, with the word apparent doing careful work, and he notes that his data might be explained by a model published by Willem de Sitter, in which light loses energy over long distances without anything actually moving. He offers the observation and declines the interpretation. Some of that was scientific caution, and Hubble had earned the right to it. Some of it, by the account of people who knew him, was that he did not want to attach his name to a claim that might be overturned. He trusted photographic plates. He did not much trust theories, and he was not a mathematician. So the most consequential graph of the 20th century was published by a man who declined to say what it meant. Someone else had already said it. 2 years earlier, in a journal almost nobody read, in a language most astronomers did not work in. And the reason that paper had sunk without trace is a story about how science actually moves, which is to say slowly, unfairly, and with a great deal depending on who happens to be in the room. In February of 1917, Albert Einstein published a paper applying general relativity to the universe as a whole. He had completed the theory only 14 months earlier. It was the first time anyone had written down equations that described the shape and behavior of all of space at once, and Einstein was, reasonably enough, the first person to try. The equations gave him an answer he did not want. General relativity says that mass and energy curve space-time, and that the curvature is what we experience as gravity. Apply that to a universe filled more or less evenly with matter, and the matter pulls on itself. Everything attracts everything. A universe like that cannot sit still. It must be either falling inward or flying apart. And the one thing it cannot do is remain the same size. Everyone in 1917 knew the universe was static, not as a hypothesis, as a background fact, the way you know the floor is solid. The stars had been in the same constellations for as long as there had been records. Nothing anyone had ever observed suggested motion on a cosmic scale. So Einstein added a term. He introduced a constant into the field equations, written as the Greek letter lambda, which behaved as a mild repulsion built into space itself, spread evenly everywhere, tuned to precisely cancel the inward pull of all the matter in the universe. With lambda set to exactly the right value, the equations permitted a static cosmos. He knew what he had done. He wrote at the time that the term was not justified by our actual knowledge of gravitation, and that he had introduced it only to make a stable distribution of matter possible. It was a patch. He described it as such, in print, and then he went on with his life. The patch was also unstable in a way he did not fully appreciate. Balancing attraction against repulsion produces an equilibrium like a pencil standing on its point. Nudge it slightly denser and gravity wins and it collapses. Nudge it slightly thinner and lambda wins and it runs away. A static Einstein universe would not have survived its own first fluctuation. That same year, the Dutch astronomer Willem de Sitter found a second solution, describing a universe with no matter in it at all, which also refused to sit still. The first person to take the equations completely at their word was a Russian who was not an astronomer. Alexander Friedmann was born in St. Petersburg in 1888, the son of a ballet dancer and a pianist. He trained as a mathematician and worked in meteorology, the physics of weather and moving fluids. During the First World War, he flew as a bombardier on the Austrian front and calculated ballistic tables for aerial bombing accurate enough that they were used operationally. He was interested in the atmosphere in a physical, hands-on way. In July of 1925, he went up in a balloon to 7,400 meters, a Soviet altitude record, to take measurements. He lost consciousness on the way down. Friedmann taught himself general relativity from the papers, and he approached the cosmological problem the way a mathematician approaches any system of equations. If a set of equations admits a family of solutions, you find the whole family. You do not select the one that flatters your assumptions. In 1922, he published 7 pages in the German journal Zeitschrift für Physik on the curvature of space. In it, he derived the general solutions for a universe that is smooth and the same in every direction. There is a family of them. Some expand forever. Some expand to a maximum size, stop, and collapse back. Some oscillate. Every single one of them changes with time. None of them are static, including Einstein's, which turns out to be a knife-edge special case of no physical importance. Einstein read the paper and published a short note declaring that Friedmann's results were mathematically incorrect. Friedmann checked his work. He found no error, because there was no error. He wrote to Einstein directly, laying out the calculation step by step, and the letter went unanswered for months because Einstein was traveling in Japan. A colleague of Friedmann's, Yuri Krutkov, eventually cornered Einstein in person in Leiden and walked him through it. Einstein published a retraction. The draft of that retraction survives, and it is worth knowing what is on it. He had originally written that while Friedmann's results were correct, they could hardly be ascribed any physical significance. Then he crossed that clause out before submitting. He conceded the mathematics. He did not concede the universe. Friedmann never learned whether he had been right. In September of 1925, a few weeks after his balloon flight, he died of typhoid fever at the age of 37, contracted, by the most common account, from unwashed fruit bought during a holiday in Crimea. His work vanished into the literature and stayed there for the better part of 2 decades, until people began going back through the old journals to establish who had seen the expanding universe first, and found that a meteorologist had derived the whole thing in 7 pages in 1922. The man who connected the mathematics to actual measurements was a Belgian priest. Georges Lemaître was born in Charleroi in 1894. He began studying civil engineering, and in 1914 he enlisted as a volunteer in the Belgian army, serving through the entire war as an artillery officer. He was in the trenches at the Yser. He was decorated with the Croix de Guerre. He came out of the war, resumed his studies in physics and mathematics, and simultaneously entered a seminary. He was ordained in 1923. He saw no conflict between the two vocations and was consistently sharp about it later in life, arguing that scripture was not a physics textbook and that physics was not a route to God, and objecting when the Pope tried to use the Big Bang as proof of creation. He held that the two were separate ways of arriving at truth and that mixing them damaged both. After ordination, he studied under Arthur Eddington at Cambridge, then went to Harvard and to the Massachusetts Institute of Technology. He was in the United States in the mid-1920s, in the middle of everything. He was present at the meeting in January of 1925, where Hubble's Cepheid result was announced. He read Slipher's velocity tables. He knew the observational landscape in a way that no European theorist did. In 1927, back in Belgium, he published a paper in the Annals of the Scientific Society of Brussels with a title that translates as a homogeneous universe of constant mass and increasing radius, accounting for the radial velocity of extragalactic nebulae. He derived the expanding universe from general relativity, independently of Friedman, and by a different route. Then, he did the thing that nobody else had done. He took Slipher's measured velocities and the best distance estimates available, and he showed that the data followed a linear relation, and he extracted the constant of proportionality. He got 625 kilometers per second per megaparsec. Hubble's paper, 2 years later, would give 500, using better distances. The same relation, from the same underlying data, published first, with the physical interpretation attached. And Lemaître went further than Hubble ever would. He pointed out that if the universe has been growing, then running the film backwards leads to a moment when everything was compressed together, and he proposed that the universe had begun as a single quantum of enormous energy, which he called the primeval atom. The paper sank without a ripple. It was in French, in a regional journal with limited circulation, and the small number of people equipped to understand it were mostly not reading it. Lemaître took the work to Einstein at the Solvay conference in Brussels later that year. Einstein listened and told him that his calculations were correct, but that his physics was abominable. That is the exact reported wording, and it is a precise summary of Einstein's position. The mathematics was fine, as it had been fine when Friedman did it. What Einstein could not accept was the idea that it described anything real, and in particular, he could not accept a universe with a beginning. Then in 1929, Hubble published his graph, and by 1930, the expanding universe was suddenly the most important open problem in physics. And Eddington remembered the paper his former student had written and arranged for it to be translated into English for the monthly notices of the Royal Astronomical Society. When the translation appeared in 1931, paragraphs were missing. Specifically, the passages where Lemaître derived the velocity to distance relation and calculated the expansion rate were absent. The English version read as a piece of pure theory, mathematically interesting, observationally disconnected. It looked as though Lemaître had produced the model and Hubble had produced the discovery. That is what astronomers believed for the next 80 years, and it hardened into the standard account. In 2011, the astrophysicist Mario Livio went looking for who had done the cutting. He found the correspondence. Lemaître had translated the paper himself, and he had removed the sections deliberately. In a letter to the editor, he explained his reasoning plainly. He did not find it worthwhile to reprint the provisional discussion of the expansion rate, because Hubble's measurements had since superseded his own. Nobody censored him. He edited himself out, on the grounds that the newer data was better, and apparently without much interest in who was credited. In 2018, the International Astronomical Union voted to rename Hubble's law as the Hubble-Lemaître law. It took 91 years. Einstein came around in 1931. He traveled to California, went up to Mount Wilson, and stood beside Hubble under the dome of the 100-inch for a photograph that became one of the defining images of 20th century science. He looked at the plates. He abandoned the cosmological constant, publishing a paper that year describing an expanding universe with lambda removed. The famous line about it being the biggest blunder of his life comes to us entirely through George Gamow, who reported it in his memoirs. It appears nowhere in Einstein's own writing or correspondence, and Gamow was a wonderful physicist and an unreliable narrator with a taste for a good story. Whether Einstein said those words is genuinely uncertain. What is not uncertain is the substance. Einstein had a theory that predicted the expansion of the universe, and he modified the theory to suppress the prediction, and the prediction turned out to be correct. It was available to him in 1917, 12 years before anyone photographed it. The name that the whole picture ended up with was an insult. In March of 1949, the astronomer Fred Hoyle was talking on BBC Radio. Hoyle disliked the idea of a universe with a beginning, preferring a steady-state model in which matter is continuously created and the universe looks the same forever. And in the course of explaining the competing view, he referred to this Big Bang idea. He always maintained afterward that he had not meant it as mockery, only as a vivid phrase for a general audience. Either way, it stuck, and the theory Hoyle spent his career opposing is now known by the name he gave it. But the equations that Friedmann and Lemaître had solved contained something that had not yet been noticed, and it answered a question that anyone hearing about the expanding universe asks within about 30 seconds. If space is stretching everywhere, why are you not stretching? The room you are in is made of space. So is the gap between the Earth and the Sun, and the gap between the Sun and the nearest star, and the gap between one atom in your hand and the atom beside it. If new distance is being generated continuously throughout the universe, it ought to be being generated here as well. And the solar system ought to be slowly inflating, and the atoms in your body ought to be drifting apart. They are not. And the reason is contained in the same equations. And it is the detail that turns the expanding universe from a slogan into something you can actually reason about. Expansion is not a force. Nothing is pushing. That distinction does almost all of the work. A force acts on objects, and if there were a genuine repulsive force operating everywhere, then yes, it would be trying to pull the solar system apart, and gravity would have to fight it continuously. But the expansion described by general relativity is not that. It is a property of the geometry, and it describes the behavior of space in regions where matter is spread thin, and nothing has taken local control. Where matter is dense, gravity has already taken control, and the geometry there is not the expanding geometry. It is the geometry of a bound system. Think of an ant standing on a stretching rubber band, holding onto a pebble that has been glued to the surface. The band grows, the pebble does not, because the forces holding the pebble together are enormously stronger than the tug of the rubber it is sitting on. The pebble simply rides. Your body is the pebble. So is the Earth. So is the solar system, and the Milky Way, and the entire local group of galaxies. These are regions where matter long ago collapsed to a stable arrangement, where the local density is far above the cosmic average, where gravity or electromagnetism or the strong nuclear force is in charge and has been for billions of years. They are not participating in the expansion at all. They dropped out of it, one by one, as they formed. The numbers make this less of a philosophical claim and more of an accounting exercise. If you calculate what the cosmological expansion would do to the orbit of the Earth around the Sun, assuming it acted on bound systems at all, you get a change of roughly 1 part in 10 to the power of 23 per year. Over the entire history of the solar system, 4.5 billion years, that accumulates to a change in the Earth's orbital radius smaller than the width of a single atom. That is the scale of the effect on anything held together. It is not that expansion is fighting your atoms and losing. It is that in the region occupied by your atoms, there is no expansion to fight. The stretching happens in the voids. It happens in the enormous near-empty spaces between clusters of galaxies, where the average density falls below a critical threshold and nothing local is in command. Those regions are where the new distance appears, and they are the overwhelming majority of the volume of the universe. There is a boundary, and we can locate it roughly. The Milky Way and Andromeda are bound to each other, which is why they are approaching rather than receding, and why they will collide in about 4.5 billion years. The local group as a whole is bound. The Virgo cluster, 65 million light-years away, is pulling on us, and we are falling toward it, but the expansion is likely to win that particular contest, and Virgo will eventually recede. Beyond that, in 2014, a team led by Brent Tully mapped the flows of galaxies in our neighborhood and identified a much larger structure that our galaxy sits within, a supercluster complex spanning around 500 million light-years, which they named Laniakea, from the Hawaiian for immeasurable heaven. It is a real structure, in the sense that the galaxies in it are all flowing in a common pattern. It is not bound. Dark energy will pull it apart, and the parts will drift away from each other. And the structure is temporary, in a way that the local group is not. So the universe stretches, and it does not tear. The expansion has never had any effect on your body, on the ground under the building you are in, or on the distance between the Earth and the Sun. It works only where nothing else is holding on. Now run the film backwards. If the voids have been growing, then in the past they were smaller. Further back, smaller still. Take that all the way, and every void closes, every cluster merges, every galaxy dissolves into the gas it formed from, and everything that now spans 93 billion light-years is compressed into a region of no great size at all, hot enough and dense enough that atoms cannot hold together. That is the beginning, and it follows from the equations rather than from anyone's preference. It is also, as soon as you look at it closely, riddled with problems. The first one concerns the temperature of the sky. The cosmic microwave background, the oldest light there is, has a temperature of 2.725 Kelvin. Point a radio telescope in any direction and you measure that same temperature, and the variations between one patch of sky and another are about 1 part in 100,000. That uniformity should be impossible. Take 2 points on opposite sides of the sky. Their present separation is around 93 billion light-years. Light from one of them has been traveling toward the other for the whole history of the universe and has covered about 46 billion light-years. It has not arrived. It will not arrive. Those two regions have never exchanged a signal, never exchanged a particle, never exchanged heat, and have had no causal contact of any kind since the universe began. Things reach the same temperature by interacting. A hot object and a cold object placed in contact will equalize, because energy flows between them until they match. That process requires contact. Two regions that have never been able to influence each other have no mechanism for agreeing on anything, and yet they agree to within a few parts in a million. This is the horizon problem. It was pointed out clearly by Wolfgang Rindler in 1956, and for the next 2 decades, the honest answer was that the universe apparently started out uniform, and no one could say why. The second problem concerns the shape of space. General relativity allows the universe to have one of 3 overall geometries, determined by how much total energy density it contains. There is a critical density, and if the actual density matches it exactly, space is flat, meaning parallel lines stay parallel, and the ordinary rules of geometry hold at cosmic scales. Above critical density, space is closed and curves back on itself. Below it, space is open and curves away. The universe we measure is flat, or so close to flat that we cannot detect any difference. That sounds like a modest result, and it is not, because flatness is unstable. In an expanding universe governed by these equations, any small deviation from the critical density gets amplified over time, rapidly. If the early universe had been a fraction denser than critical, gravity would have overwhelmed the expansion, and the whole thing would have collapsed within a fraction of a second. A fraction thinner, and the expansion would have outrun gravity so thoroughly that no gas cloud would ever have collapsed into a star. Work backwards from a universe that is flat today, after 13.8 billion years of amplification, and you find that the density at the earliest moments must have matched the critical value to about 1 part in 10 to the power of 60. That is a pencil balanced on its point, still standing, after the entire age of the cosmos. This is the flatness problem, and Robert Dicke laid it out plainly in 1969. Neither problem was a contradiction in the equations. Both were assumptions. The standard model of the Big Bang could accommodate a universe that started out uniform and precisely tuned, in the sense that it did not forbid it. It simply had nothing to say about why. There was a third problem, and it came from particle physics rather than cosmology. In the 1970s, theorists were building grand unified theories, attempts to show that the strong, weak, and electromagnetic forces are three faces of a single force that separated as the universe cooled. Those theories worked well in several respects and produced one awkward prediction. In 1974, Gerard Hooft and Alexander Polyakov independently showed that theories of this kind necessarily produce magnetic monopoles, isolated magnetic north poles with no south, extremely massive, produced in enormous quantities during the transition. They should be everywhere. Estimates suggested monopoles should be about as common as protons. Nobody has ever detected one. Not in 1974, and not since, despite decades of dedicated searches. Three problems then, sitting in the foundations. The sky was too uniform, the geometry was too finely balanced, and a class of particle that should have flooded the universe was entirely absent. For a long while these were filed as things that would presumably be explained eventually. Then a postdoc with no permanent job and a growing suspicion that his career was going nowhere sat down to work on the third problem and discovered that a single mechanism disposed of all three at once. Alan Guth was 32 years old and running out of road. He had a doctorate from the Massachusetts Institute of Technology in particle theory, and since finishing it, he had held a sequence of temporary positions: Princeton, then Columbia, then Cornell, then the Stanford Linear Accelerator Center. 4 postdoctoral appointments. In academic physics, that is not a career trajectory. That is a warning. He had published respectable work, and nothing that had made anyone urgently want to hire him permanently, and he had a wife and a young son, and a growing awareness that the field might simply be finished with him. In November of 1978, while he was at Cornell, Robert Dick came to give a talk. The subject was the flatness problem, the pencil balanced on its point. Guth was not a cosmologist and had no professional reason to care. He went anyway, and the argument lodged somewhere and stayed there. A colleague at Cornell, Henry Tye, had been pushing him to work on magnetic monopoles. Guth was reluctant. Tye persisted. Eventually they began calculating how many monopoles a grand unified theory would produce in the early universe, and the answer, as expected, was catastrophically too many. The question then became how to get rid of them, and the natural place to look was the phase transition itself. Here is the physics, and it is worth going carefully because everything else rests on it. A field is not an exotic idea. It is just a quantity that has a value at every point in space. The temperature in a room is a field. So is the magnetic field around a bar magnet. In particle physics, every particle is an excitation of an underlying field, and fields have energy associated with their configuration. Ordinarily, a field settles into whatever configuration has the lowest energy, the way a ball rolls to the bottom of a valley. But a landscape can have more than one valley, and a field can get stuck in one that is not the lowest. Physicists call that a false vacuum. It looks like empty space. It behaves like empty space in most respects, and it is not the true ground state. There is a lower valley elsewhere, and the field will eventually find it, but for a while it sits where it is. Guth was working out what happens if the universe cools quickly enough that a field gets caught in a false vacuum before it can transition properly. That is supercooling, and it is the same phenomenon as water chilled below freezing that has not yet turned to ice. What he found is that a false vacuum has an unusual property. It has a fixed energy density, the same amount of energy in every cubic meter, and crucially, that density does not decrease as the region expands. Ordinary matter thins out when you give it more room. This does not make more space, and the new space arrives already carrying the same energy density as the old. In general relativity, that combination produces negative pressure, and negative pressure, in Einstein's equations, gravitates in reverse. Instead of pulling space together, it pushes it apart. It is precisely the behavior of the cosmological constant that Einstein had invented and discarded. Not similar to it, the same mathematical form and vastly stronger. A region in that state does not expand steadily. It expands exponentially, doubling in size, then doubling again in the same interval, then again, with each doubling taking as long as the last. On the night of the 6th of December, 1979, Guth worked through what that would mean for a universe of any initial shape. Exponential expansion flattens geometry. Take a curved surface and enlarge it enormously, and any patch of it becomes indistinguishable from flat, the way the surface of the Earth appears flat to someone standing on it. Whatever curvature the universe started with would be driven towards zero, and not approximately towards zero, driven so hard towards zero that the residual curvature today would be undetectable. The flatness problem was not a coincidence to be explained, it was a prediction. At the top of the notebook page, he wrote the words "spectacular realization" in capitals and drew 2 boxes around them. The page still exists. The line beneath it says that this kind of supercooling can explain why the universe today is so incredibly flat, and therefore resolve the fine-tuning paradox pointed out by Bob Dick. The next morning, he set a personal record for the fastest bicycle ride from his house to his office at the Accelerator Center, 9 minutes and 32 seconds. That detail is preserved because he wrote it down too. The horizon problem fell in the same stroke, and it fell more elegantly. Before inflation, the region that would become our entire observable universe was not large. It was a patch small enough that light could cross it comfortably, which meant it had every opportunity to reach a uniform temperature by ordinary means, the way any small system does. Then the patch inflated, and it inflated so violently that it was stretched to encompass everything we can now see. The 2 regions on opposite sides of the sky did touch. They touched before inflation began, when they were adjacent, and inflation carried them apart faster than any signal could follow. They match because they were once the same thing, and the monopoles, the problem he had started with, were diluted into irrelevance. Whatever was produced before inflation got spread across a volume so much larger that the expected number remaining anywhere near us drops to something on the order of 1 in the entire observable universe. 3 problems, 1 mechanism, 1 night. The numbers required are the part that resists intuition. To do the necessary work, the universe has to grow by a factor of at least 10 to the power of 26 during inflation, and it has to do it in around 10 to the minus 32 seconds. Physicists measure this in e-folds, where 1 e-fold is growth by a factor of the mathematical constant e, roughly 2.718. Inflation needs at least 60 e-folds, which corresponds to about 87 doublings in size, one after another, all inside a period vastly shorter than the time it takes light to cross a proton. Start with a region far smaller than a proton, a quantum speck governed by uncertainty. Let it inflate. It emerges somewhere in the region of a meter across. That single fact contains the entire growth factor. If you took a grain of sand and enlarged it by the same proportion, it would be substantially larger than the observable universe. But the scale is not the part that matters most. The early universe was not perfectly smooth, and it could not have been. Quantum mechanics forbids perfect smoothness. A field cannot have exactly the same value everywhere because the uncertainty principle guarantees that its value fluctuates, and at the smallest scales the field driving inflation was jittering constantly. Tiny random variations in energy density appearing and vanishing. Inflation stretched those fluctuations along with everything else. A jitter that began smaller than a proton was pulled out to millions of light-years across. And once it had been stretched beyond the distance light could travel, it stopped being able to smooth itself out. It froze. It became a permanent feature, a region of very slightly higher or very slightly lower density than its surroundings. When inflation ended, those regions were the starting conditions of everything that followed. Slightly denser patches pulled in slightly more matter, which made them denser still, which pulled in more, over billions of years. They became the gas clouds that became the first stars. They became the galaxies, the clusters, the filaments and walls and voids that make up the large-scale structure of the universe. Every galaxy in the sky is a quantum fluctuation that got enlarged and then never had a chance to relax. The pattern of matter across billions of light-years is the frozen imprint of random quantum noise from the first fraction of a second. Guth's model had a serious flaw, and he knew it when he published. The problem was how inflation stops. If the field is sitting in a false vacuum driving exponential expansion, something has to get it out. And in Guth's original version, the field escaped by quantum tunneling in scattered bubbles. The bubbles would form, but the space between them would still be inflating exponentially, faster than the bubbles could grow and merge. You would end up with isolated pockets in an eternally inflating void, with no way to produce a smooth universe full of matter. He called this the graceful exit problem. He put it in the paper. He published anyway, in Physical Review D in January of 1981, because the successes were too substantial to sit on, and he judged that someone would find the fix. The fix took about a year. André Linde, working in Moscow, and Paul Steinhardt and Andreas Albrecht, working independently in Pennsylvania, arrived at the same modification. Instead of the field being trapped in a false vacuum and tunneling out, let the field start high up on a very gently sloping potential and roll slowly down it. While it rolls slowly, the energy density stays nearly constant and inflation proceeds. When it reaches the bottom, it oscillates and dumps its energy into a bath of particles and radiation. That last step is the important one, because it means inflation does not precede the hot Big Bang. Inflation causes it. The heat of the early universe is the energy of the inflaton field being released as it settles. The Big Bang is inflation ending. Linde's situation in the Soviet Union was its own small story. He had the idea in 1981, but Soviet publication required official clearance and took months. In the interim, Stephen Hawking visited Moscow and gave a talk, and Linde, who spoke English well, was asked to translate it into Russian live for the audience. Partway through, Hawking began explaining why the new idea did not work, and Linde had to stand in front of a room full of his colleagues and translate a detailed criticism of his own unpublished work, sentence by sentence, out loud. He then spent considerable time convincing Hawking that the criticism was mistaken. It was. In 1983, Linde went further with a model he called chaotic inflation, which removed the requirement that the universe begin in any special state. Any region that happens to have a scalar field with a high enough value will inflate, regardless of what the surroundings are doing, which raises an implication that Linde and Alexander Vilenkin both noticed, and that Guth later took up as well. If inflation is driven by a field that fluctuates quantum mechanically, then in some regions the fluctuation pushes the field back up the slope rather than down it, and those regions keep inflating. Inflation ends locally, in patches, while continuing elsewhere. And because the inflating regions grow exponentially and the finished regions do not, the inflating portion always dominates. Inflation, once started, may never stop globally. It may still be going on right now, somewhere, at a rate that outstrips everything. We will come back to what that implies. For the moment, there was a much more pressing matter. Inflation was an elegant story about the first fraction of a second, and elegant stories about unobservable epochs are cheap. The question was whether it had left anything behind that could be measured. It had. And the instrument that would find it was, at the time Guth was writing, a horn-shaped antenna in New Jersey that 2 engineers had spent a year trying to clean. The prediction came first, and it was ignored for 17 years. In the late 1940s, George Gamow was working on the question of where the chemical elements came from. Gamow was Russian-born, physically enormous, fond of practical jokes, and one of the few people at the time taking the early universe seriously as a physics problem rather than as speculation. If the universe began hot and dense, he reasoned, it was a nuclear furnace, and the elements should have been cooked in it. Working with his doctoral student Ralph Alpher, he produced a paper on the origin of the elements. Gamow, who could not resist, added the name of Hans Bethe to the author list purely so that the paper would read Alpha, Bethe, Gamow. Bethe had contributed nothing and agreed to it good-naturedly. Gamow arranged for it to be published on the 1st of April, 1948. The joke has outlasted much of the physics, but the physics was substantially right about hydrogen and helium, and Alpha, working now with Robert Herman, followed the reasoning one step further. If the universe was once that hot, it was filled with radiation, and that radiation could not have gone anywhere. It would still be here, cooled by the expansion of space, stretched from the wavelengths of a furnace down into the microwave. Alpha and Herman calculated what temperature it should have now. They got about 5 Kelvin. They published the prediction. Nobody built an instrument to look for it. Nobody, so far as anyone can determine, seriously discussed doing so. The technology to detect it existed. The prediction was in the literature with a number attached. And for 17 years, the most important observational test in cosmology sat unexamined, partly because radio astronomers and nuclear theorists did not read each other's journals, and partly because the whole notion of a universe with a beginning was still regarded by many as slightly disreputable. In 1964, two Soviet astrophysicists, Andrei Doroshkevich and Igor Novikov, published a paper noting that the radiation should be detectable and identifying, by name, the specific instrument in the world best suited to finding it. They named a horn antenna at Bell Laboratories in Holmdel, New Jersey. Nobody at Bell Labs read the paper. The antenna had been built in 1959 for Project Echo, an early experiment in satellite communication that involved putting a large aluminized balloon in orbit and bouncing radio signals off it. Later it was used with Telstar. It was a horn reflector, about 20 feet across, shaped something like an enormous ear trumpet lying on its side, mounted so it could be steered, and it had one quality that made it unusual. Because of its geometry, it picked up almost nothing from the ground around it. It listened only where it was pointed. By 1964, the communications work had moved on, and the horn was available for radio astronomy. Two young researchers took it over. Arno Penzias had been born in Munich in 1933. His family were Jewish, and in 1939, his parents put him and his younger brother on a train to England. He was 6 years old. His parents got out separately, and the family reassembled in New York, where his father worked as a leather cutter in the Bronx. Penzias took a physics degree at City College and a doctorate at Columbia. Robert Wilson had grown up in Houston, the son of an oilfield chemist, taking radios apart. He had done his doctorate at Caltech. Their plan was to measure the faint radio emission from the halo of the Milky Way, which required knowing exactly how much signal the instrument itself contributed. So they pointed the horn at a patch of sky they expected to be quiet, and measured what came back, expecting nothing. They got a hiss. It was low. Converted into a temperature, it came out at about 3.5 Kelvin above absolute zero. It did not vary with the time of day, which ruled out the sun. It did not vary with the season, which ruled out anything in the solar system. It did not change when they pointed at different parts of the sky, which ruled out the galaxy, since the galaxy is a disk and looks different in different directions. It was simply there, identical everywhere, unchanging, as though the sky itself were faintly warm. They assumed the instrument was broken, which is the correct assumption to make. They spent the better part of a year on it. They checked every connection, every amplifier, every length of cable. They pointed the horn at New York City to see whether urban radio noise might be leaking in. They taped over the riveted joints in the aluminium in case the seams were radiating. They cooled the reference load with liquid helium to make the comparison as clean as possible. And they discovered that a pair of pigeons had taken up residence inside the horn and had coated portions of the interior with what Penzias, in the published account, described as a white dielectric material. The pigeons were trapped and relocated. They flew back. They were dealt with more permanently, which Penzias later said he did not much enjoy. The horn was cleaned out. The signal did not change. At this point, they had a persistent, isotropic, unexplained excess and no framework for it, because neither of them was a cosmologist and neither had encountered the Alpha and Hermann prediction. They started asking colleagues. Penzias mentioned it in passing during a telephone conversation with Bernard Burke, who said that he had heard about a preprint circulating from a group at Princeton, about 40 kilometers away. The Princeton group was Robert Dick, Jim Peebles, David Wilkinson, and Peter Roll. They had independently reconstructed the argument that Alpha and Hermann had made without knowing about it, and they had reached the same conclusion. If the universe began hot, the radiation is still here, and it should be a few Kelvin. They were, at that moment, building an antenna on the roof of the Princeton Physics Building to look for it. Penzias telephoned. He described the excess temperature, the isotropy, the year of failed attempts to remove it. Dick listened for a while without saying much. Then he hung up the phone, turned to the people in the room with him, and said that they had been scooped. The two groups published in the same issue of the Astrophysical Journal in 1965. Penzias and Wilson wrote 2 pages describing an excess antenna temperature at a wavelength of 7.35 centimeters. Their paper contains no cosmology at all. It reports a measurement and includes a single sentence noting that a possible explanation is offered in a companion letter. The Princeton group wrote the companion letter, explaining what it was. What it was is the light released when the universe became transparent. For the first roughly 380,000 years, the universe was too hot for atoms to hold together. Electrons could not stay bound to nuclei. Everything was a plasma, a fog of free charged particles, and photons cannot travel far through a plasma because free electrons scatter them almost immediately. Light existed. It went nowhere. Every photon was absorbed and re-emitted continuously, in a fog with no visibility. Then the expansion cooled things below about 3000 Kelvin, and electrons could finally hold on to protons, and neutral hydrogen formed throughout the universe more or less at once. The fog lifted. Suddenly there were no free electrons to scatter from, and every photon that had been trapped in that plasma was released to travel in a straight line, and most of them have been traveling ever since without hitting anything at all. That release happened everywhere simultaneously, which is why it comes from every direction. It is not an object in the sky, it is a moment in time, and we see it in every direction, because in every direction, far enough away, you are looking back to when the fog lifted. The light left at a temperature of about 3000 Kelvin, which is orange, roughly the color of a dim filament lamp. If you had been present, the entire sky would have glowed that color, in all directions, with no dark anywhere. It arrives now at 2.725 Kelvin. Its wavelength has been stretched by a factor of about 1090, which means that since the moment it was released, the universe has grown by that same factor. That number is one of the most precisely known quantities in cosmology, and it comes directly from comparing the temperature it left at with the temperature it arrives at. There are around 400 of these photons in every cubic centimeter of space. That includes the cubic centimeters inside you. They pass through the roof, through the walls, through the bed, through your body, in numbers that run to the billions every second, and they have been doing so continuously for your entire life and for the entire existence of your species. You cannot feel them. There is not remotely enough energy in them to be felt. But they are the single most abundant kind of photon in the universe, outnumbering all the light from all the stars that have ever existed by a factor of billions, and they are older than every atom in your body. For a while there was a way to see them indirectly. On an old analog television tuned to a channel with no station, a small fraction of the static, well under 1%, was this radiation. Not a metaphor. The antenna was collecting photons from the plasma of the early universe, and the tube was drawing them on the screen as noise. Penzias and Wilson received the Nobel Prize in 1978. Alpha and Herman, who had predicted the thing 17 years before it was found, received nothing. Alpha was bitter about it for the rest of his life, and it is difficult to argue that he was wrong to be. He was awarded the National Medal of Science in 2005. At the age of 80, this had to be accepted on his behalf because he was too ill to travel, and he died 2 years later. The horn antenna is still standing in Holmdel. It was designated a National Historic Landmark. The signal it found is the strongest single piece of evidence that the universe had a hot, dense beginning, and it was discovered by 2 men who spent a year trying to get rid of it. But there was something wrong with it, and the problem was that it was too good. The radiation was uniform, too uniform. If the early universe had been genuinely smooth, matter would have stayed evenly spread, because there would have been nothing for gravity to grab onto. No region would ever have become denser than its neighbors. There would be no stars, no galaxies, no planets, and no one to point an antenna at anything. There had to be structure in it, faint but present. Inflation predicted exactly what that structure should look like, down to its statistical shape. Finding it would take a satellite, 25 years, and a rocket explosion that nearly ended the whole project. The proposal went to NASA in 1974, and it was one of about 150 that arrived that year. John Mather was a young postdoc at the time, and the idea he and his colleagues submitted was to put an instrument above the atmosphere and measure the oldest light with a precision that no ground-based experiment could reach. The atmosphere is the enemy here. Water vapor glows faintly in the microwave, and it absorbs the signal coming from space, and no matter how carefully you correct for it from the ground, it sits between you and the thing you are trying to measure. Get above it, and the sky goes quiet. The mission that eventually emerged was called the Cosmic Background Explorer, and it took 15 years to build. 15 years is a long time to hold a team and a design together, and the design nearly did not survive its own success. The Explorer was originally meant to launch on the Space Shuttle. Then in January of 1986, the Shuttle Challenger broke apart shortly after launch, killing all 7 people aboard, and the entire shuttle fleet was grounded for years. The Explorer had no ride. The team found a way to rework the satellite to fit on a Delta rocket, which meant stripping mass out of a spacecraft that had been designed for a completely different launcher, without compromising the instruments. They managed it. The Explorer went up on a Delta in November of 1989 into a polar orbit about 900 kilometers high, from which it could scan the entire sky as the Earth turned beneath it. It carried 3 instruments. One mapped infrared dust. The other 2 are the ones that matter here. Mather's instrument was designed to measure the spectrum of the oldest light with extreme accuracy, to test a single specific prediction. If the light really was the afterglow of a hot, dense early universe, then it should have an extremely particular spectral shape, the shape that physicists call a blackbody, the shape emitted by anything that is simply hot and in equilibrium with itself. Any deviation from that shape would mean something more complicated had happened, and the simple, hot Big Bang picture would be in trouble. The instrument compared the sky against a precisely controlled internal reference at a known temperature, switching between them many times a second, cooled by liquid helium to eliminate its own thermal glow. The result came back within weeks of launch. In January of 1990, Mather stood up at a meeting of the American Astronomical Society and showed the spectrum. The measured points sat on the theoretical blackbody curve so exactly that the error bars were smaller than the width of the line drawn on the graph. There was no visible scatter, there was no deviation. It was, and remains, the most perfect blackbody spectrum ever measured in the laboratory or in nature. The room stood up and applauded, in an echo of the applause for Slipher 76 years earlier, and for the same underlying reason. A theory had made a hard prediction, and the universe had met it without argument. The temperature came out at 2.735 Kelvin, later refined to 2.725. The early universe had been hot, dense, and in near-perfect thermal equilibrium. That much was now settled. The second instrument was the difficult one. It was designed by a team led by George Smoot, and its job was to find the departures from uniformity, not to confirm that the sky was smooth, which was already known, but to find the tiny places where it was not quite smooth, the faint variations in temperature from one patch of sky to another that had to exist if the structure of the universe was ever going to form. The scale of the challenge is worth stating plainly. The variations being sought were around 30 millionths of a Kelvin, against a background of 2.7 Kelvin, about 1 part in 100,000. And they had to be dug out from underneath every competing signal. The Milky Way's own microwave glow, the motion of the solar system through the radiation, which makes one side of the sky look slightly warmer than the other by an amount far larger than the signal being hunted. The instrument's own imperfections. Smoot's team measured differences between pairs of points on the sky over and over for 2 years and accumulated the differences and slowly subtracted away everything that was not primordial. They kept the analysis quiet because they understood what they had and understood how badly a mistake would damage it. On the 23rd of April, 1992, Smoot presented the result at a meeting of the American Physical Society. The map was a mottled oval, blue where the sky was 100,000th of a degree cooler, and red where it was 100,000th of a degree warmer, and the pattern was real, and its statistical properties matched what inflation had predicted, a particular kind of randomness, present at all scales, close to what theorists call scale invariant. The spectrum of the primordial fluctuations was there, in the data, in the shape the theory required. These were the seeds. Every galaxy that exists grew from one of the denser patches on that map. The structure of the entire universe was visible in its embryonic form, 30 millionths of a degree of unevenness in the oldest light. Then Smoot said the sentence that he has been quoted on ever since. He told a reporter that if you are religious, it is like looking at God. Physicists winced. The phrase went around the world within a day. It irritated many of his colleagues, including some on his own team, who felt it dragged theology into a measurement that did not need it, and who also felt that the credit was being concentrated on one person when the work had involved a very large team. The tension was real, and some of it never fully healed, but the measurement was sound, and it stood. And in 2006, John Mather and George Smoot shared the Nobel Prize for it. Mather for the spectrum, Smoot for the fluctuations. It is generally regarded as the mission that turned cosmology into a precision science, the point at which it stopped being a field where quantities were known to within a factor of 2 and became a field where they were known to several decimal places. The explorer saw the fluctuations. It could not see them sharply. Its resolution was about 7 degrees, roughly 14 times the width of the full moon. So the map was real but blurry, a photograph of the right thing taken slightly out of focus. To read the detailed information encoded in the pattern, you needed to see the small scales, and that required going back. The next mission was the Wilkinson Microwave Anisotropy Probe, named after David Wilkinson, one of the Princeton physicists who had been building a rooftop antenna to look for the radiation when Penzias telephoned. He worked on this mission too, and it was named for him after his death. Rather than orbit the Earth, it was sent about 1.5 million kilometers out to a point called the second Lagrange point, where it could sit in a stable position on the night side of the Earth, shielded from the Sun, the Earth and the Moon all at once, in the thermal quiet it needed. It launched in 2001, and it mapped the whole sky with a resolution around 35 times finer than the Explorer had managed. The pattern resolved into detail, and the detail could be read, and reading it produced numbers. The universe is 13.77 billion years old. That figure came out of these maps, and it is worth registering that we know the age of the universe to better than 1% from the statistical pattern of a temperature map. The composition came out too. About 5% of the universe is ordinary matter, the stuff of stars and planets and people. About 27% is dark matter, which has mass and gravity but does not interact with light. And about 68% is something else entirely, driving the expansion, which we will come to. The map also encoded the shape of space, and it said flat, not approximately flat, flat to within a couple of percent, which was the strongest confirmation yet of the central prediction of inflation. Then in 2009, the European Space Agency launched Planck, the third-generation instrument, to the same distant point beyond the Earth. Its detectors were cooled to 1/10 of 1 degree above absolute zero, the coldest known objects in space at the time, colder than the natural universe around them, because the natural universe around them was 2.7 Kelvin, and they needed to be colder than the thing they were measuring. Planck mapped the oldest light at a resolution and sensitivity that has not been surpassed and probably will not be for a long time. Its final results, released in stages through 2018, are the reference against which cosmology still works. The universe is flat to within a couple of tenths of a percent. The age, the composition, the fluctuation spectrum, all pinned down to a precision that would have seemed like fantasy to the people applauding Mather in 1990. And there was structure in the pattern that carried its own story, a set of frozen sound waves, which turned out to be a second and completely independent way of measuring the whole thing. There is music frozen into the oldest light, and it is not a metaphor. Before the fog lifted, when the universe was still a plasma, it was not silent. The matter in it was being pulled 2 ways at once. Gravity pulled it together, drawing it toward the denser patches the seeds inflation had planted. And the pressure of the radiation pushed it back out, because photons trapped in the plasma resist being compressed. Pull in, push out, pull in, push out. That is an oscillation. It is, physically, sound. Pressure waves moving through a medium, which is the definition of sound, propagating through the plasma of the entire universe at more than half the speed of light. The universe rang like a struck bell for 380,000 years. it is possible to work out what note it was ringing at. The oscillations in the plasma were true pressure waves, and pressure waves have frequencies, and the dominant frequency of the early universe corresponds, if you shift it up by the enormous factor needed to bring it into human hearing, to something far below the lowest note a piano can play, a deep tone tens of octaves beneath anything an ear could register. The physicist John Cramer once did exactly that calculation, scaling the frequencies up so they could be heard, and produced a recording of the sound of the first fraction of a million years, a low, evolving roar that rises and shifts as the universe expands and the waves stretch. It is not a reconstruction of something poetic. It is the actual spectrum of the actual oscillations, moved into a range a person can hear. Then the fog lifted, the electrons bound to the nuclei, the pressure vanished because the photons were suddenly free, and the oscillations stopped mid-swing. Wherever a given wave happened to be in its cycle at that instant was frozen in place, printed into the pattern of hot and cold spots in the light that was released. You can read the frozen music. When you analyze the map of the oldest light and ask what sizes of spot are most common, you do not get a smooth answer. You get a series of peaks, preferred sizes, harmonics, exactly as a musical instrument produces a fundamental note and a series of overtones. The plasma had a fundamental tone, set by how far a sound wave could travel between the beginning of the universe and the moment the fog lifted, and it had overtones above it. The position of the first and loudest peak is the crucial one, because it tells you the true physical size of that fundamental wave. And if you know the true size of something, and you measure the size it appears in the sky, the relationship between the two depends on the geometry of the space the light crossed to reach you. In flat space, the spot appears at about 1 degree across. In positively curved space, the geometry magnifies it and it looks larger. In negatively curved space, it looks smaller. It is the oldest surveying trick there is, a triangle with a known base, used to measure the shape of the universe. The spots come in at 1 degree. Space is flat. The sound waves in the plasma turn out to be one of the most powerful tools we have, and they were discovered by looking for structure in a map and finding that the structure was harmonic. There is a companion to this, and it took until 2005 to detect directly. Those same sound waves left an imprint not just in the light, but in the distribution of matter. At the moment the fog lifted, each initial dense point sat at the center of a spherical shell of matter that the sound wave had pushed outward, at a radius set by how far the wave had traveled. That radius is frozen too, and it means that galaxies today are very slightly more likely to sit about 490 million light-years apart than at other separations. A faint preferred distance, printed across the whole universe by sound in the plasma. It is called the baryon acoustic oscillation, and it functions as a ruler of known length laid across cosmic history. Measure how big that preferred separation appears at different distances, and you are measuring how much the universe has expanded at different times. It is completely independent of the Cepheids and the supernovae and everything in the distance ladder, and it agrees with them, which is the kind of agreement that makes a science solid. The oldest light gave us the age, the composition, the shape, and the seeds. It gave us 2 independent rulers. It confirmed the central prediction of inflation. It also handed us a crack, and the crack has been widening for a decade. There are 2 ways to measure how fast the universe is expanding today, and they no longer agree. The first way works forward from the oldest light. Take the Planck map, feed it the physics of the plasma and the sound waves, and the standard model of cosmology predicts, among everything else, the current expansion rate. That prediction comes out at about 67.4 kilometers per second per megaparsec, and it is extraordinarily precise. The second way works the way Hubble did, only vastly refined. Build a ladder, use parallax for the nearest stars, use Cepheids calibrated against that parallax, use those Cepheids to calibrate type Ia supernovae in nearby galaxies, and use the supernovae to reach deep into the expanding universe. Adam Rees, who we will meet properly in a moment, has led this measurement for years, refining every rung of the ladder. It comes out at about 73 kilometers per second per megaparsec. The difference is roughly 9%, and 9% might sound like the ordinary disagreement of a young science, except that both measurements have been sharpened relentlessly, and instead of converging as the errors shrank, they have stayed apart while the error bars closed in around them. The gap is now statistically significant, at a level that cannot be waved away as bad luck. It has a name. It is called the Hubble tension, and as of the mid-2020s it is unresolved, and it is one of the most actively worried over problems in physics. Either one of the two measurements has a subtle error that many independent teams have failed to find, despite looking very hard, or the standard model of cosmology is missing something. A new kind of particle in the early universe. Dark energy that changes over time rather than staying constant. Some piece of physics between the oldest light and now that we have not yet identified. The honest position is that nobody knows, and that the disagreement is being taken seriously, precisely because both numbers come from careful work that has survived a great deal of scrutiny. What the oldest light could not tell us, on its own, was what most of the universe is made of, and how it behaves, and where it is going. For that, cosmology needed a different kind of object, not the smooth glow of the early universe, but individual explosions, each one as bright as a galaxy, scattered across billions of years of cosmic history, each one a measuring point. And when two teams set out in the 1990s to use those explosions to measure how fast the expansion was slowing down, they found, to their considerable alarm, that it was not slowing down at all. By the early 1990s, the question seemed almost settled in advance, and only the number was missing. The universe was expanding. Gravity pulls. So the expansion had to be slowing down, as everything in it tugged backward on everything else. The only real question was how much, and the answer would decide the ending. If there was enough matter, gravity would eventually halt the expansion, reverse it, and pull everything back into a final collapse. A big crunch that mirrored the Big Bang. If there was too little, the universe would coast outward forever, slowing but never stopping. The whole fate of everything came down to a single measurement of how fast the slowing was happening. The tool for measuring it was a particular kind of exploding star. A type Ia supernova begins with a white dwarf, the dead core of a star like the Sun, about the size of the Earth but with a mass comparable to the Sun, so dense that a spoonful weighs tons. A white dwarf is held up not by heat, but by a quantum effect, the refusal of electrons to be packed into the same state, a pressure that has nothing to do with temperature and does not fade as the star cools. But that pressure has a limit. In 1930, a 19-year-old named Subramanian Chandrasekhar worked it out on the ship, carrying him from India to England to begin his doctorate. He calculated that a white dwarf cannot support itself above about 1.4 times the mass of the Sun. Past that, the electron pressure fails. When Chandrasekhar presented the result in London a few years later, Arthur Eddington, the most eminent astrophysicist alive, and the man who had confirmed general relativity, stood up and ridiculed it publicly, declaring that there should be a law of nature to prevent a star behaving in such an absurd way. Chandrasekhar was right, and Eddington was wrong, and it took the field years to say so out loud. The humiliation was public, and it was delivered by the most powerful figure in the discipline, and it landed on a young man far from home who had done nothing but the arithmetic correctly. Chandrasekhar, wounded, eventually moved to the United States, joined the University of Chicago, and largely turned away from the subject that had made his name, moving through one area of astrophysics after another, over a long and extraordinarily productive career, mastering a field, writing the definitive book on it, and then leaving it for another. He received the Nobel Prize for that shipboard calculation 53 years later, in 1983, when he was 73 years old. The spacecraft that now carries the most detailed X-ray eyes we have ever put into orbit is named the Chandra X-ray Observatory, in his honor, and it has photographed the hot gas around the very objects his limit describes. Here is why the limit matters for measuring the universe. If a white dwarf in a binary system pulls matter off its companion, it grows, and as it approaches that 1.4 solar mass limit, it detonates. Because it always detonates at essentially the same mass, by essentially the same process, every type Ia supernova releases close to the same amount of light. They are standardizable. Correct for how fast each one fades, and you have an object of known true brightness, briefly as luminous as an entire galaxy, visible across a large fraction of the observable universe. Known true brightness is everything, because comparing it to how bright the supernova appears gives the distance, and the supernova's redshift gives how much the universe has expanded since it exploded. Collect enough of them across enough of cosmic history, and you can trace the expansion itself and read off whether it was faster or slower in the past. Two teams set out to do this, and they did not like each other much. The Supernova Cosmology Project, based at the Lawrence Berkeley National Laboratory, was led by Saul Perlmutter, a physicist who had come at the problem through automation, building software, and survey strategies to find supernovae reliably rather than by luck. They started first. In the late 1980s, the High Z Supernova Search Team formed a few years later, led by Brian Schmidt, an American astronomer based in Australia, and it was heavy with people who had spent their lives studying supernovae as objects and were skeptical that Perlmutter's group understood the stars well enough to trust their results. The analysis lead was a young researcher named Adam Rees. The rivalry was sharp, occasionally bitter, and it turned out to be the best possible circumstance. Because when the two competing teams arrived at the same impossible answer independently, it was very hard to blame the answer on either team's mistakes. The work itself was grinding. Supernovae are unpredictable and brief. You cannot point at a galaxy and wait. You photograph thousands of galaxies, come back 3 weeks later, photograph them again, and subtract one image from the other, so that everything steady cancels out, and only new points of light remain. Then you race, because a supernova rises and fades in weeks, and you need the biggest telescopes in the world to get a spectrum confirming its type and a redshift. And telescope time is booked months ahead, and the weather does what it wants. By 1997, both teams had enough distant supernovae to plot against the prediction. The expectation was clear: distant supernovae, whose light left long ago when the universe was expanding faster, should appear slightly brighter, slightly closer than a coasting universe would place them. Because the expansion had been decelerating, Rees ran the analysis for the High Z team in the autumn of 1997, and the distant supernovae came out wrong. They were too faint. They were further away than they should have been, not closer, as deceleration required. Further, the only way to put them that far away was for the expansion to have been slower in the past and to have sped up since. The universe was not decelerating, it was accelerating. Something was pushing space apart, and its influence was growing. Rees has described sitting with the result and not believing it, going back through the analysis looking for the error, running it with different assumptions and different subsets of the data, and watching the answer refuse to go away. He wrote to a team member around then that the data required something almost none of them wanted to be true, and that the result was making him wish he had never touched the problem. Meanwhile, the Perlmutter team, working entirely separately with different supernovae and different software, was converging on exactly the same conclusion, and initially resisting it just as hard. The two teams published within a few months of each other, the High Z team in the spring of 1998, the Supernova Cosmology Project shortly after. Two rival groups, who would each have been delighted to catch the other in an error, reporting the same thing. The expansion of the universe is speeding up. The thing doing the pushing got the name dark energy, and the name is mostly an admission of ignorance. The simplest description of it is the term Einstein had invented and thrown away. A cosmological constant, an energy that belongs to space itself, the same density in every cubic meter, that does not thin out as space expands because it is a property of the space rather than a substance sitting in it. Make more space, and you make more of this energy, at the same density as before. So the total quantity of it grows as the universe grows, which produces a runaway. More space means more dark energy, means faster expansion, means more space still. The acceleration feeds itself. This is what the 68% from the oldest light turned out to be. More than 2/3 of everything is this. The 5% that is ordinary matter, the 27% that is dark matter, all the galaxies and all the stars and all the dark matter holding them together are together less than 1/3 of the contents of the universe, and the largest component by far is a property of empty space that we detected only by watching distant explosions come out fainter than they should. Perlmutter, Schmidt, and Rias shared the Nobel Prize in 2011. There is a number attached to dark energy that is worth ending on, because it is either the deepest mystery in physics or a sign that we are asking the question wrong, and no one can currently say which. Quantum theory suggests that empty space should not be empty. It should froth with fields that have energy even in their lowest state, and that energy should behave exactly like a cosmological constant, and it should therefore be measurable as the acceleration of the universe. So physicists calculated how much energy the vacuum should contain and compared it to how much dark energy is actually out there. The prediction is too large. It is too large by a factor of about 10 to the power of 120, a 1 followed by 120 zeros. It is the worst quantitative prediction in the history of physics, wrong by more orders of magnitude than there are atoms in the observable universe. And it sits at the center of our current picture because the thing we cannot calculate is the thing driving the entire future of the cosmos. We know dark energy is there. We have measured how much of it there is to 2 significant figures. We have essentially no idea what it is, and our best attempt to derive it from first principles misses by a margin that is difficult to write down. There is a second thing about dark energy that is almost as strange as the first, and it gets less attention. For most of cosmic history, dark energy was irrelevant. In the early universe, matter was packed tightly, and its density was enormous, and dark energy, being a fixed density spread thinly through space, was utterly negligible by comparison. As the universe expanded, matter thinned out, its density falling, while dark energy held steady, and only relatively recently, in the last few billion years, did the thinning density of matter fall below the constant density of dark energy, at which point dark energy took over and the expansion began to accelerate. The strange part is the timing. Of all the epochs in the history of the universe, we happen to be living in the brief transitional window when matter and dark energy are roughly comparable, when the handover is actually taking place. 1 billion years earlier, and matter still dominated. Many billions later, and dark energy will dominate completely. We are here for the crossover. Whether that is a coincidence or a selection effect because this is the era when galaxies and observers can exist, or a clue that our understanding is incomplete, is genuinely unknown. It is called the coincidence problem, and it sits alongside the vacuum energy problem as a thing the current picture describes precisely and explains not at all. That is the current frontier, stated honestly. And where dark energy takes the universe from here is the last part of the story. Everything you have ever seen is old. The light from this room reached your eyes a few billionths of a second ago, which is close enough to now that it does not matter. The light from the moon left it about 1.25 seconds ago. Sunlight is 8 minutes old, so the sun, you can see, is always the sun of 8 minutes past. And if it winked out, you would have 8 minutes of ordinary afternoon before the sky noticed. The nearest star beyond the sun is 4 years away at the speed of light. The center of our galaxy is 27,000 years in the past. Andromeda is 2.5 million years old by the time its light lands on you, which means you are seeing it as it was before your species existed. Look far enough, and you are looking early enough that the thing you are looking at may no longer be there. This is not a limitation of telescopes. It is the structure of the universe. Because light takes time to arrive, distance is the same thing as pastness, and to look out into space is to look back into time, with no way to separate the two, which means the phrase observable universe describes something specific. It is the sphere around us from which light has had time to arrive since the beginning. Its edge, about 46 billion light-years away in present distances, is not a wall. There is nothing there. It is simply the furthest back we can see, the distance at which we are looking all the way to the moment the fog lifted, and beyond which the light has not yet had time to reach us. That boundary is called the particle horizon. The universe certainly continues past it. We just cannot see past it, because the light from further out is still on its way, and in a great many cases it will never arrive at all, because there is a second horizon, closer in, and it is the one that decides the future. In a universe that was merely coasting, the particle horizon would keep growing forever. Wait long enough and light from further and further away would keep reaching you, and the observable universe would keep enlarging, taking in more galaxies with every passing eon. But our universe is not coasting, it is accelerating, and acceleration reverses that. It sets a hard limit on what can ever reach us. There is a distance, right now, beyond which any light setting out toward us today will never arrive, not because it is too far in the ordinary sense, but because the space between us and it is expanding faster than the light can cross it. The photon travels toward us at the speed of light, and the intervening space grows by more than the photon covers, and the gap widens even as the photon flies. It is a runner sprinting along a road that is being stretched faster than she can run, and no matter how long she runs, the finish line recedes. That distance is the cosmic event horizon, and it sits about 16 billion light-years away, which is less than half the radius of what we can currently see. Sit with what that means, because it is strange. We can see galaxies whose present distance is far more than 16 billion light-years. We see them because their light left long ago, when the universe was smaller and they were closer, and the acceleration had not yet built up. That ancient light made it across before the door closed. But the galaxies as they are now, this instant, are beyond the event horizon, and anything they emit now will never reach us. We see their past. We are permanently cut off from their present. If a civilization on one of those worlds is looking back at the Milky Way tonight, the light it is sending will cross empty space forever and never land here. We are already, in the only sense that matters, out of contact, exchanging nothing but antique light emitted before the separation became total. Consider a specific object. There is a galaxy called GNZ11, found in 2016 with the Hubble Space Telescope by a team led by Pascal Auge, and for a while, it was the most distant galaxy known. Its light left it about 400 million years after the Big Bang, when the universe was 3% of its present age. When that light set out, the galaxy was a little over 2 billion light-years away. Today, after 13.5 billion years of expansion, its present distance is around 32 billion light-years, far outside the event horizon. If a star in that galaxy exploded at this moment, we would never learn of it. The light would set out and lose the race. And GNZ11 is not unusual in this. Every galaxy beyond a redshift of about 1.5 is already past our event horizon. The overwhelming majority of the galaxies whose ancient light fills our telescopes are objects whose present selves we will never see again. Stop for a moment and put yourself at the edge of what can be seen. You are looking out at a galaxy near the limit of the observable universe, and the light entering your eye left it when the cosmos was an infant, before the sun, before the earth, before the atoms in your hand were forged. The galaxy that sent it has spent the intervening billions of years living a life you will never witness. It has made stars and lost them. It may have merged with others, changed shape, gone dark. None of that has reached you, and none of it ever will. You are holding a photograph of a stranger who died long ago, taken when they were young, and the photograph is the only thing of them that will ever arrive. That is not a rare situation at the edge of the sky. It is the normal one. Almost everything we can see is a message from something we have already lost. And because the expansion is accelerating, the event horizon is drawing inward over time, in the sense that fewer and fewer galaxies remain inside it. One by one, over the coming eons, the galaxies we can still see will cross that line. Their light will stretch redder and redder, dimmer and dimmer, until it thins below anything an instrument could register. And then they will be gone. Not destroyed, simply carried beyond the reach of any possible signal. Follow that forward, and the far future of the sky is bleak in a very particular way. The Milky Way, Andromeda, and the few dozen smaller galaxies of the local group are gravitationally bound, so the expansion cannot separate them. They will fall together instead. Andromeda is already approaching, and in roughly 4.5 billion years the two great galaxies will collide and, over billions of years more, merge into a single elliptical galaxy. Astronomers have nicknamed the eventual result Milkomeda. Around that time, the Sun will be swelling into a red giant and the Earth will be uninhabitable, so no one will watch the merger from here. But it will happen. Everything outside the bound local group will recede and cross the horizon. The great clusters, the Virgo cluster, the Laniakea flows, the whole cosmic web of galaxies stretching across billions of light-years, all of it will slide beyond reach. The oldest light itself will redshift away, its wavelength stretching from millimeters to meters to kilometers, its temperature falling toward absolute zero, until eventually its waves are longer than the observable universe can contain, and it effectively ceases to exist as a signal. And here is the part that genuinely unsettles the cosmologists who work on it. Imagine an astronomer on a planet in the merged Milky galaxy 100 billion years from now. She looks out with the finest instruments her civilization can build, and she sees her own galaxy, an island of stars, and around it, in every direction, nothing. No other galaxies, no cosmic web, no oldest light, no redshift to measure, because there is nothing left in the sky that is receding. No evidence of any kind that the universe is expanding, that it ever expanded, that it began in a hot, dense state, that there were ever 2 trillion other galaxies. She would have the same telescopes we have and better. She would be a careful scientist. And every observation available to her would point to a single, static island of stars, sitting in an infinite empty void, eternal and unchanging. She would conclude, correctly given her evidence, and completely wrongly given the facts, that this was all there had ever been. Lawrence Krauss and Robert Scherer spelled this out in 2007. It is not speculation. It is what the standard model of cosmology, the same model confirmed by the oldest light and the supernovae, predicts about the far future if you simply let it run, which places us somewhere very specific in the history of everything. We exist late enough that galaxies and stars and planets and minds have had time to form, and early enough that the evidence of the universe's origin and structure is still in the sky, still arriving, still readable. Both conditions have to hold at once for a civilization to be able to work out where it came from, and they only both hold for a relatively narrow slice of cosmic time, and we are inside that slice. We happen to be able to see it. The astronomer in Milky will not. That is not a lesson about anything. It is simply where in the story we are standing, and the position is temporary, and the window does not stay open. But if the observable universe is a bubble of visibility inside something larger, the obvious question is how much larger, and whether the something larger contains anything as strange as we would fear or hope. The measurement that decides how large the universe is came from a balloon over Antarctica. By the late 1990s, the shape of space had been narrowed down but not nailed. The Cosmic Background Explorer had shown the sky was consistent with flatness, but its resolution was too coarse to measure the crucial first acoustic peak, the one whose angular size reads out the curvature directly. What was needed was a sharper map of a patch of sky, and the cheapest way to get above the atmosphere without a satellite was to hang a telescope from a balloon and fly it around the South Pole. The experiment was called Boomerang, for balloon observations of millimetric extragalactic radiation and geophysics, led by Paolo de Bernardis in Rome and Andrew Lang in the United States. In the Antarctic summer, a stratospheric balloon caught by the circular polar winds will drift in a loop around the pole and come back roughly to where it started, which lets a payload stay aloft for a week or more and then be recovered. In the flight over the turn of 1998 into 1999, the balloon carried its telescope in a long, slow circle for 10.5 days, mapping a patch of sky in the microwave, and then the gondola parachuted onto the ice, and a recovery team went out and retrieved the hard drives. The map showed hot and cold spots, and the typical spot came in at about 1 degree across. That is the flat answer. Parallel rays had stayed parallel. Space, to the precision Boomerang could reach, is flat. Flatness is a statement about the density of the universe. The equations define a critical density, and if the actual density equals it, space is flat, and the ratio of actual to critical is written as the quantity omega, which then equals 1. Boomerang measured omega to be 1 within a few percent, and the Wilkinson probe and Planck later drove the uncertainty down to a couple of tenths of a percent. The universe sits on the knife edge, at the critical density, flat as far as we can measure. And a flat universe, in the simplest reading, is infinite. A closed universe, denser than critical, curves back on itself and has a finite volume, like the surface of a sphere, but in 3 dimensions, unbounded but not endless. A flat universe does not curve back. It extends without limit, in every direction, forever. If the measurement is telling the truth and space is exactly flat, then the universe does not stop anywhere. And the 93 billion light-years we can see is not most of it, or a large fraction of it, or any fraction of it that can be sensibly written down. It is essentially nothing. A single grain against an endlessness. There is a caveat that has to be stated, because it is the honest position. A measurement can never prove exact flatness. It can only place the curvature below some threshold. And there will always be a threshold below which a very gently curved, very large but finite universe would be indistinguishable from an infinite flat one. We cannot ever step far enough back to see whether the whole thing eventually curves. So the choice between an infinite universe and one that is merely too large to measure may never be settled by observation. Inflation predicts flatness, and the data are consistent with exact flatness, and that is as far as certainty goes. But take the infinite case seriously for a moment, because it leads somewhere that sounds like fantasy and follows from arithmetic. If space is infinite, then it contains infinitely many regions the size of our observable universe. And here is the pivot. A region the size of our observable universe can only be arranged in a finite number of ways. That is not obvious, so go slowly. Our observable universe contains a large but finite amount of matter, something like 10 to the power of 80 particles. Quantum mechanics says that the possible states of a finite region are not continuous but discrete, countable. There are unimaginably many ways to arrange 10 to the power of 80 particles in a volume this size, but the number of ways is finite, enormous, and finite. So you have infinitely many regions, and only finitely many possible ways for a region to be. There is only one way for that to work. Every possible arrangement has to repeat, not once, infinitely often. Somewhere out there, at a distance that can be estimated, is a region identical to this one. The same galaxy, the same planet, the same room, the same arrangement of every atom in the air and in your body, down to the last particle. A copy of you, in that copy of this room, reading this same sentence, with every star overhead in the same position. The physicist Max Tegmark worked out roughly how far away the nearest such copy should be, using the counting of possible quantum states. The distance is a number that cannot be meaningfully compressed. It is 10, raised to the power of 10, raised again to the power of 115. Written in ordinary digits, it would not fit in the observable universe. But it is a specific finite distance, not infinity, and in an infinite flat universe the copy is not a possibility. It is a certainty. The only open question is how far. Slightly nearer than that unimaginable distance, in fact, are the near copies. Regions almost identical to this one, differing in a single detail. A version where one word on this page is different. A version where a decision you made this year went the other way. A version where the same is true of every person on the planet. The differences accumulate with distance, and every variation that is physically possible is realized somewhere, an infinite number of times over. Whether such a copy is you is not a question physics can answer. It has the same memories, the same sense of being a single continuous self, the same conviction that it is the original. So do you. Physics only says that the arrangement of particles is identical, and falls silent on everything that seems to matter about the question. It is worth saying clearly that infinity is not, on this picture, full of wonders. It is overwhelmingly full of near emptiness. The vast majority of those regions the size of our observable universe contain no life, no planets worth the name, nothing but thin gas and the slow drift of matter that never assembled into anything. The copies of you are real, if the universe is infinite, but they are needles scattered through a haystack so large that the distances between the interesting regions make the distance between galaxies look like a single step. Infinity produces everything, and mostly it produces nothing, at staggering length. And there is a second, separate route to a multiplicity of worlds, which comes not from the size of space, but from inflation itself. Recall that inflation, once it starts, may not stop everywhere at once. The field driving it fluctuates, and in some regions the fluctuation keeps it high and inflating, while in others it rolls down and the local Big Bang begins. The finished regions become universes like ours, pockets where inflation ended and matter condensed and structure formed. The unfinished regions go on inflating, faster than the pockets can spread, forever spawning new pockets. This is eternal inflation, and it produces not copies of our universe but genuinely other universes, each one a bubble in an endlessly inflating background, each one causally sealed off from all the others. Our entire observable universe, the whole 93 billion light-years of it, would be the interior of a single one of these bubbles. Beyond it, unreachable, forever out of contact, an unbounded and growing number of others. If string theory is right that the laws of physics can settle in a vast number of different configurations, some enormous number often quoted as 10 to the power of 500, then different bubbles could have different physics, different particle masses, different strengths of the forces, different values of that dark energy that is driving us apart. Most such universes would be sterile, unable to form atoms or stars or chemistry. We find ourselves in one that permits all of that, not because it was arranged for us, but because the sterile ones have no one in them to notice where they are. That last argument is called the anthropic principle, and a great many physicists dislike it intensely, because it feels like surrender, like giving up on explaining why the constants have the values they do, and settling for observing that if they were different, we would not be here to ask. It may nonetheless be the correct answer. The universe is under no obligation to explain itself in a way we find satisfying. It is only obliged to be consistent with the fact that we are in it. And here is the difficulty that hangs over all of it. The multiverse, in both forms, may be a real consequence of theories that are themselves well supported, and it may also be permanently untestable, because everything it predicts lies beyond every horizon, sealed off by the same acceleration that is carrying the visible galaxies away. A prediction you can never check sits uneasily at the border of science, and where exactly that border falls is not currently agreed, and may not be for a long time. What can be said is smaller and stranger and more certain. The same measurements that gave us the age and the composition and the shape of the universe also, if taken at face value, imply that it does not end, and that somewhere in its endlessness this exact moment is happening again, and that we will never be able to reach it or confirm it or do anything with it at all, except know that the arithmetic requires it. Everything ends, and the universe has several ways of ending, and the one we appear to be heading toward is the slowest and the quietest. Start with the stars, because the stars are already living on a clock. Star formation peaked long ago. It reached its height about 10 billion years ago, when the universe was young and gas was plentiful, and it has been declining ever since, as the gas gets used up and locked into stellar corpses that never give it back. The rate today is a small fraction of what it was. The universe has already made most of the stars it will ever make. The stars burning now will go out on their own timescales. The largest and brightest burn fast and die in millions of years. The Sun has about 5 billion years left. And the smallest stars, the red dwarfs, which are by far the most common kind, sip their fuel so slowly that they can burn for tens of trillions of years, far longer than the current age of the universe. They will be the last lights. When the last red dwarf finally cools and fades, roughly 100 trillion years from now, the era of starlight ends. No new stars will form, because the gas will be too thin and too cold to collapse. The galaxies will go dark, not suddenly, but star by star, over a span of time that dwarfs everything that has happened so far. What remains after that is a long inventory of cold remnants. White dwarfs, cooling toward black. Neutron stars, doing the same. Black holes. Dead planets, orbiting dead stars in dead galaxies. Drifting in a universe still expanding, still accelerating, spreading everything further and further apart. And even the remnants do not last. There is a suspicion, not confirmed, that the proton itself is unstable. Many grand unified theories predict that a proton will eventually decay, with a half-life of at least 10 to the power of 34 years, an interval so long that in the entire history of the universe so far, essentially none has had time to happen. Experiments deep underground have been watching enormous tanks of water for years, waiting to catch a single proton dying, and have not yet seen one, which tells us only that the half-life is very long, not that it is infinite. If protons do decay, then over a vast enough span, every atom in every cold remnant will dissolve, and the white dwarfs and neutron stars and dead planets will slowly evaporate into a thin drift of leptons and radiation. The black holes outlast even that. In 1974, Stephen Hawking showed that black holes are not entirely black. Through a subtle quantum process at the event horizon, they radiate extremely slowly, and therefore they lose mass, and therefore they eventually evaporate. The timescale is beyond comprehension. A black hole, the mass of the Sun, would take about 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies, millions or billions of times the mass of the Sun, take something like 10 to the power of 100 years. But they do it. One by one, over that unimaginable stretch, the black holes flicker out in a final faint burst of radiation, the last events in a universe that has otherwise gone still. After that, nothing. A thin, cold, ever-thinning soup of photons and light particles, drifting apart forever in the dark, at a temperature falling asymptotically toward absolute zero, but never quite reaching it. No structure, no energy differences left to do anything with, no events. This is the heat death, sometimes called the Big Freeze, and it is what the standard picture predicts, the straightforward consequence of a dark energy that stays constant and an expansion that never reverses. It is not a catastrophe, it is an exhaustion. The universe does not end in fire or collapse. It runs down, like anything else that runs, until there is nothing left that can happen. That is the likeliest ending. It is not the only one on the table, because it depends on dark energy staying exactly constant, and we do not actually know that it does. Dark energy is described by a single number that relates its pressure to its density. If dark energy is a true cosmological constant, that number is exactly -1, and you get the slow freeze. But if it is even slightly more negative than -1, if dark energy is not constant but is instead strengthening over time, the ending is entirely different and far more violent. That version is called the Big Rip. If dark energy grows, its repulsion eventually overwhelms not just the expansion, but everything holding matter together. First, the galaxies are torn from the cosmic web. Then, as it strengthens further, individual galaxies are pulled apart, and then solar systems, planets ripped from their stars. Then the planets themselves come apart, and then molecules, and then atoms. And in the final instant, space is expanding so violently within every atomic nucleus that the nuclei are shredded, and the universe ends, everywhere at once, in a finite time. The earliest estimates for such a scenario put it a few tens of billions of years in the future. Current measurements put that number very close to -1, close enough that the rip looks unlikely. But the error bars have not entirely ruled it out, and there is recent survey data hinting that dark energy might not be perfectly constant, which, if it holds up, would reopen the question. There is a third ending, unrelated to dark energy, that could in principle happen at any moment, including during this sentence, though it almost certainly will not. It concerns the Higgs field, the field that gives particles their mass. Measurements of the Higgs and the top quark suggest, tentatively, that the Higgs field may not be sitting in the lowest possible energy state. It may be in a false vacuum, the same kind of metastable configuration that drove inflation, stable for now but not truly stable. If that is the case, then somewhere, someday, a quantum fluctuation could nucleate a tiny bubble in which the Higgs field drops to its true lowest state. Inside that bubble, the laws of physics would be different, the masses of particles altered, ordinary chemistry impossible, and the bubble would expand outward at the speed of light. That last detail is the merciless one. Because the bubble wall travels at light speed, no signal could outrun it, which means nothing could ever warn you. There would be no bright light on the horizon growing closer. The bubble would arrive at the exact instant its light did, and the transition would sweep through the Earth and everyone on it faster than a nerve could fire. This is vacuum decay, and it is not a prediction that it will happen. It is a possibility the mathematics permits, with a probability in any given place and time so small that it is genuinely nothing to worry about. But in an infinite universe, somewhere, right now, at some unreachable distance, the calculation says such bubbles are nucleating. The acceleration that isolates us also protects us, carrying them away faster than they can arrive. The oldest ending of all, the one that dominated cosmology before the discovery of acceleration, has quietly dropped off the list. The Big Crunch, in which gravity halts the expansion and pulls everything back into a final collapse mirroring the Big Bang, was for decades the elegant symmetric option, and some hoped it might even bounce and begin again, a universe without end. But a crunch requires the expansion to reverse, and dark energy is doing the opposite, driving it faster. Unless dark energy someday switches from repulsion to attraction, which nothing in the data suggests, there will be no crunch and no bounce. The universe will not collapse back into a beginning. It will expand, and cool, and thin, and fade. All of these numbers are so far beyond human experience that they stop meaning anything as quantities. 10 to the power of 100 years is not a duration anyone can feel, but the shape of it can be felt if you let it. The universe had a beginning, and it will have an end. And the middle, the part with stars and planets and light and things that notice things, is a brief, bright interval between two darknesses, and we are in it now. There is one thing that connects the beginning to the end, that was there at the start and will still be crossing space when almost everything else is gone. It is passing through this room as you listen. It has been traveling since before the Earth existed, and it brings us back to where the night began. The photon from the beginning of the night is still traveling. It left its galaxy 13 billion years ago, when the universe was young and thick with forming stars, and it crossed a space that was stretching, and its wavelength stretched with it, from ultraviolet down through the visible colors, through the infrared, into the microwave, growing longer with every million years it flew. It carried no information about an outside, because there was no outside. It was never moving through the universe toward an edge. It was moving through a geometry that was complete in itself, that contained everything there was, and needed nothing beyond itself to grow into. The question that opened the night has an answer now, and it is the same answer it was at the start, only now it has some weight behind it. Where is the universe expanding into? Nowhere. The question assumes a container, a room that space is filling, an outside that the inside is advancing toward. There is no container. Space is not a thing inside a larger thing. Space is the largest thing, the only arena there is, and when it expands, it is not moving into anywhere. It is making more of itself. New distance appears between the galaxies not because they are traveling apart through some pre-existing emptiness, but because the emptiness itself is being generated, continuously, everywhere, including in the space between you and the far wall of the room you are in quantities so small there that nothing you own will ever be affected. That is the whole of it. The universe creates its own room as it goes, and there is no outside to the room. And the search for an outside is a habit of mind we brought with us from a world of boxes and skins and walls, a map that does not match the territory. The same sky that carries that photon carries the oldest light, the afterglow of the moment the fog lifted, 380,000 years after the beginning. It is 2.725 Kelvin. It fills every cubic centimeter of space, including the ones your body occupies. 400 photons in every cubic centimeter, billions of them passing through you every second. And it has been doing that for your whole life, without your ever once noticing. It is older than the Earth, older than the Sun, older than every atom, heavier than hydrogen and helium, all of which were forged inside stars that formed long after this light was already on its way. It asks nothing of you. It simply passes through and continues, and will keep passing through and stretching and cooling for billions of years, until its waves grow longer than the space that holds them, and it fades from the universe entirely. We are here in the interval when it can still be seen. That is the thing worth holding on to, at the end. The universe made a stage out of itself, and lit it, and for a while, a long while by human reckoning, and a vanishingly short one by its own. The lights are on, and the action is visible. We arrived late enough that galaxies had formed, and stars had cooked the atoms we are made of, and there was ground to stand on and eyes to see with. And we arrived early enough that the evidence is still in the sky. The receding galaxies, the redshift, the oldest light, the frozen sound, all of it still arriving, still legible. Both had to be true at once, and they will not both be true forever. And they are true now. We have used the interval. We measured the speed of the galaxies from a cold dome in Arizona and built a ruler out of pulsing stars from a room full of glass plates in Massachusetts. We found the afterglow by accident with an antenna full of pigeons and confirmed it with a satellite that had to be rebuilt after a rocket exploded. We traced the expansion with exploding stars and found it speeding up when we expected it to slow. And we do not know what is doing the speeding. And we have said so plainly. We have measured the shape of space with a balloon over Antarctica and found it flat, and followed the flatness to an infinity we can never reach, that may contain this exact moment happening again, that we can never confirm. We know a great deal. We do not know what most of the universe is made of. We do not know what came before the beginning, or whether before is even a word that applies. We do not know if the expansion will freeze the universe slowly or tear it apart, though the slow freeze looks likelier. We do not know if there is anything beyond our single bubble, and we may never be able to find out. The honest inventory of what we do not know is long, and it is not a failure. It is the edge of the map, drawn accurately, which is the most a map can do. The photon that began this story is still going. Its wavelength is still stretching, its energy still dropping, and it will keep traveling long after this planet is gone, never reaching an edge, never leaving the universe, because there is no edge, and there is nowhere to leave to. It is, and always was, exactly where it belongs. Inside the only thing there is, moving through space that is quietly, endlessly, making more of itself.